Hello Year 9s, Mrs Elliott's hand again. Today we are revising chapter 4 of the GCSE book, and that's all about handling data. So first of all, we're just going to talk about the two main types of data that you come across. You come across one type of data that's called discrete data, and the other one is called continuous data. And basically, discrete data can take only specific values, e.g. whole numbers. So if you ask somebody how many siblings they've got, they can't have 1.5 siblings, they will just tell you they've got 1, 2, 3, 4 or 0. The other thing that discrete data could be, it could have a quality to it, qualitative data. So it could be eye colour, something like that. Have you got blue eyes, brown eyes, etc. So that's discrete data, okay? Specific values, whole numbers, how many of something. Or continuous data is the other type. And continuous data, I like to think of as can be measured on a scale. So if I was to ask you how tall you are, you could tell me that you're 1.62 m, 1.63 m, 1.64 m, 1.65 m, and you probably could be even more precise than that. You could say you're 1.6573 meters tall if you were very, very precise. So continuous data is measured on a scale and therefore can take any value. Discrete data can only take very specific values, whole numbers usually, or qualities, things like eye colour. Okay, so that's the types of data that you can have. Now, the ways that we have for presenting data, for discrete data, we can use things like a bar chart. Here's a bar chart. Sometimes bar charts can be a bit fancy. So here's my bar chart. So these are my categories down here. So they might be how many siblings, number of siblings. And up here we put our frequency. That means the actual number of. Yeah. And so it could be bars that actually look like bars. You could put your bars the other way around. So you'd have your frequency here and your categories there. You can do fancy things like if you were saying how many brothers and sisters do you have, you could divide your bars into brothers and sisters, sort of type thing. Or into the boys in your class and the girls in your class, how many have they got? That's probably a better way of doing it, actually. You can do that sort of thing. You can also do things like you can put bars next to each other to represent sort of different groups. Yeah. Bars don't have to actually be bars. They could just be lines drawn on a graph like that. But one of the key things about this, the way you present discrete data in this sort of form, is that they're all separate from each other. There should be gaps in between them. Yeah. We will look later at continuous data. With continuous data, those bars can actually move right next to each other and form what we call a histogram, but we'll do that in a minute. Another way of presenting data that can be discrete data, if you're looking at the numbers of things, is in a pie chart. So pie charts. So the thing with pie charts is that you just have to remember what we've looked at in chapter 3, actually, about the total angle within a pie chart. So the total angle within this circle is 360 degrees. And so what you can do with your data is say, how much data have you got altogether? What's the total of your data? How many data items have you got? So if we say number of data items equals n, and then each of those data items takes up that many degrees, 360 over n degrees of your pi, of your circle. So for example, let's just do a little example. I don't know, let's make something up. Always a mistake with me, actually. So I'm going to go for number of siblings. I'm going to go for 0, 1, 2, and 3. Let's pretend in this group that nobody's got more than 3 siblings. And then frequency, number of people with that number of siblings. So let's say we've got a group of 12 people altogether. 12 people. So let's say of those 12 people, 3 have got no siblings. We'll say we've got 4 have got 1 sibling. Let's say that we've got 3 who've got 2 siblings and 2 people have got 3 siblings. Okay, so we've got 3, 7, 10, 12 children altogether in this group of that we're looking at. So now we want to look at the angle that they represent on the pie chart. So angle on the pie chart. So here you would say, right, in total we've got 12 children. So each child gets 1/12 of 360 degrees. So that's going to be 30 degrees, isn't it, each? And here we've got 3. So they're going to have 90 degrees. That's our first category. Our second category is going to be 360 over 12 times 4, which is 120 degrees. Our third category, we know 360 over 12 times 3 gives you 90 degrees again. And my last one, give myself a bit more space here. My last one is going to be my 30 degrees, 360 over 12. And this time it's going to be by 260. Quick check to make sure you've got your calculations right. Altogether I've got 90 plus 120, that's 210, plus 90 is 300, plus 60 is 360 degrees. So if I was to plot these on my pie chart, I would start with a dot in the middle. If you've drawn it with a compass, you'll have a natural dot in the middle there anyway. And what you will be wanting to do is make sure that you draw a line. I usually draw mine either up to the top or out to the side. And with a protractor, you would measure your angles. So for my 0 siblings, I've got 90 degrees. For my 4 siblings, I've got 120 degrees, so that would be 90. So 120 is going to take me sort of somewhere about there. For my 3 siblings, I've got 90 degrees again, so something like that. And then for my 3 siblings, 60 degrees. So I'm going to just label mine. So I'm going to write number of siblings as my title. And I am going to have, so 0 siblings, 1 sibling, 2 siblings, 3 siblings there. Okay. Now, probably one of the more common thing that happens on pie charts is that instead of writing those in, you put a key together. Okay, so I'm going to actually just sort of shade this in a bit. So I'm going to say that purple means 0 siblings. I'm going to say that black means 1 sibling. I'm going to say blue. I've got a blue pen, so I'll do a blue. Blue means 2 siblings. Blue equals 2. And then I'll just do a sort of an empty box to indicate that no colour in at all means 3 siblings. So in that case, I wouldn't need to have the numbers written in because I've got my colours doing the job for me. I would say there's a bit of a debate sometimes about whether or not you need to put your angles in. I think you need to have written your angles very clearly somewhere. So if you haven't written them very clearly on your frequency table. This is a frequency table that I've drawn here. If you haven't written them very clearly here, then write them on here. So that's a 90 degrees, that's a 90 degrees, that's 120 degrees, and that's 60 degrees. I would say you can't have too much information on your pie chart. Okay, so the idea of splitting your 360 degrees into a certain angle per person or per data item. In this case, we had 12 data items, so everybody had 360 divided by 12, which is 30 degrees each. And then 30 times 3 is my 90, 30 times 4 is my 120, 30 times 3 is 90 again, and 30 times 2 is 60. Okay, so pie charts, you do need to be able to draw them. You need to be able to show your workings on your frequency table for each of the angles, and you do need to be able to draw your angles correctly using a protractor. The only other thing I would say they might ask you on pie charts, they might show you a pie chart of one class of children with the number of siblings, say, and draw another pie chart with another class, and they would show the different from the key you would know the different numbers of siblings, and they would say, does this pie chart show that class A has more children with 2 siblings than class B? And you've got to be careful on those, because you've got to know how many children or how many data items your pie chart represents. And if this pie chart just represents 12 children and the other pie chart represents 32 children, then clearly you've got to look at the data in the table to know what the frequencies are. You can say what the proportions are. You could say that the proportion of children in both classes is a quarter, say, with no siblings, but because there are different numbers of children in each class, obviously that's going to be a different number. Yeah, so they might try and catch you out with a question like that. Okay, right. Other things about data that you need to be able to do. You need to be able to calculate some specific measures that relate to your data. So we're going to stick with our discrete data for the moment, and I'm going to give you some numbers, and we're going to look at some specific measures in relation to them. Okay, so these are going to be ages of people in a lecture. Okay, so there's a lecture going on. Somebody's giving a lecture, and we've got some ages of the people there. So there's a 53-year-old, a 74-year-old, a 29-year-old, a 32-year-old, a 67-year-old, a 53-year-old, a 99-year-old, a 62-year-old, a 34-year-old, a 28-year-old, a 27-year-old, a 27-year-old, a 27-year-old, 1, 2, 3 of those, a 64-year-old, and a 27-year-old. Okay, so what we have got is a set of discrete data. These are specific numbers. They're not in decimal form or anything. They're actual specific values. And I've just said they're ages of people in a lecture. They could be ages of people at a birthday party. Could be somebody's 27th birthday, couldn't it? Or 28th birthday. Anyway, so there are people sitting in a room, and these are their ages. And what we want to do is just get an idea of what the averages are for this. Yeah, what's the average age of the people in the room? And we've got quite a few different measures for average, and we need to know their mathematical definition, and we need to know how to make comparisons perhaps between the ages of people in this room and ages of people in another room, say. So the measures that we use, we call some of them averages, and the first one that we're going to have a look at is the mean. Okay, now the mean, the way you calculate the mean, I'm sure you do remember this, it's the sum of all of your values divided by the number of values that you've got. So it's probably most people's idea of an average. Yeah, most people's definition of an average would be exactly that, the sum of all the values divided by the number of values. And I'm just looking around on my desk for my calculator, which I seem to have mislaid. So I'm just going to get my spare. So I'm going to add up all of these values. Okay, hopefully I'll do it correctly. So some of the values that I've got a 53, a 74, a 29, a 32, a 67, a 53, a 99, a 62, a 34, a 28, a 27, a 27, a 27, a 64, and a 27. Now, what I am just going to do before I press the equals button here, is I'm just going to count how many values I've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I've got 15 values, and I'm going to need that number anyway, down at the bottom here, because I'm dividing by the number that I've got. But I'm just going to check on my calculator that I've got 15 values, because it's easy to put these incorrectly into your calculator. So I'm just going to go back to the beginning of mine and just see if I've got them all. Oh, I think hang on, where did I start? I started on the 53. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, I have got 15 values on mine, so hopefully I've got the right ones. And mine add up to 703. So 703 divided by 15, that gives me 46 point, I've got 86666, so I'm going to round to one decimal place. I'm going to do 46.9, and that's to one decimal place, or 3 significant figures. Yeah, remember our definition. One decimal place, because I had 866, I went for 86. And so it was going to be a 9. Significant figures, 1, 2, 3 significant figures. Does that seem reasonable looking at the data that I've got there? Well, actually, yeah, it is in the middle of the data, isn't it? I've got some lower end data at 27, upper end data 99, and quite a few values in the middle here. Yeah, that does seem like a reasonable value. Okay, so whenever you do a calculation of a mean, just check to yourself, is this reasonable? Okay, just in case we've put the numbers in incorrectly. So check, reasonable, question mark. Okay, so that's a mean, and you do need to know how to calculate a mean, gentlemen. Next measure of average, or centralness, centrality we sometimes call it, we're going to call the mode. Now the mode is the one that you see the most. Equals value you most see. Yeah. Now I think looking at this data, it's fairly obvious which one is the most seen. Just looking at it, we've got 1, 2, 3, 4 values that are 27. And we don't have as many of that as of any others. But what I'm going to do, because it will be useful to me anyway for my next calculation, I am just going to write my data in order. And if you write your data in order, sometimes on questions where it's less obvious where the mean is, where the mode is, which one you can see the most, once you write your data out in order, it does become more obvious. So I'm going to try and fit it all across my board here, and I'm going to write it in order, and as I do it, I'm going to tick off my data, okay, so that I don't miss any. So I've got a 27, 27, 27, and 27. So I've got 4 of them. 1, 2, 3, 4 27s. Okay, just going to put little commas next to them so you can see where each one finishes. Okay, now I've got a 28 there, so I'm going to do that one next. 28. I've got a 29. I've got a 32. I think that's my next one. Sometimes it's good if you've got a little bit of space on your page, which I haven't really got. If you've got a bit of space, leave a bit of space just in case you have to slot one in. 32 is the next one. I haven't got a 33, but I have got a 34, so I'm ticking that. Notice I'm ticking them That is so that I get them all in and I don't forget any. So 34, next one up from 34. Nothing in the 40s. No people in this lecture in their 40s. So I'm going into the 50s. I've got two 53s. Put those in. 53 and 53. Have I got anyone in their 60s? Yes, I have. I've got a 62-year-old and a 64-year-old. A 62 and a 64. They're both done. Then I've got a 67-year-old. Oh, I'm not going to quite fit these in, am I? 67-year-old. I'm going to go up just onto my next line. And then I've got a 74-year-old and a 99-year-old, my last two. Checking that I've ticked them all. And I'm also going to check that I've written them all down. So I should have 15 values. 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15. So they're all there. Okay. Do that check, chaps, because otherwise you get it wrong. And it's for a silly reason that you've just missed something out. So I can see very clearly now that the value most seen, my mode, is 27. Yeah. So it isn't in the middle of my data. So I've got to be careful with using a mode to describe my data. It is the one there's the most of. And as I said, this could have been not a lecture, but a 27th birthday party. Would make sense that there were some 27-year-olds there. Anyway, right. Okay, so that's the mode, mean and mode. Next one we need to have a look at. Our next definition is the median value. Our median value is our middle value from our set of data. So we've got 15 data items here. So our 15, to get our middle data item, if you've got an odd number, you would add 1 to it, that means 16, and you would say half of that, that takes you to data item number 8. 1, 2, 3, 4, 5, 6, 7, 8. That's my middle data item. Now, if you wanted to, you could say, well, to find your middle, you don't have to do that n plus 1 thing. You could say that's one at each end. And then that's another one at each end. That's another one at each end. So I've got 3 off each end, 4 off each end, 5 off each end, 6 off each end, 7 off each end. And that gets you to the 34 in the middle. Yeah. So when you've got an odd number of data items, it will be your middle value. Yeah. So in this case, it's definitely 34. If you had an even number of data items, so let's just say that we had one more data item on the end. If we had one more data item on the end, we'd have 16 data items, and our median would therefore fall between those two values. If that was the case, you just need to find the halfway point between those two. And the way to find the halfway point between two numbers is to add them together and divide by 2. So they would be 87 divided by 2. That would give me 43.5, would be halfway between those. Okay, so just bear that in mind. Right, okay, but we don't need that on this one because we've got a middle value. Yeah, and I would say note, go halfway between values if have an even number. Okay, so those 3 are our measures of centrality or centralness or average. Okay, and most of the time with averages, mostly they ask you for a mean, but they could easily ask you for a mode or a median. Other things that they could ask you for, so that gives you an idea of where your data lies, what's in the middle of it, or what's the most common data item, the one you see the most. The other things they could ask you about is how spread out your data is. So measures of spread, okay? Measures of spread, there are 2 main ones that we look at GCSE. Measures of spread, just going to check on my camera that you can see this written at the bottom of the page. Yes, you can. Measures of spread. Oh, hang on. I'll just move my board a little bit that way. You can see the word measures. and mode and everything else. There we go. That's a bit better, isn't it? Right, measures of spread. So the easiest one is the range. So literally that is your largest data item minus your smallest data item. Okay, so in this case, because we've got our data in order, and you do need, for both this median and for the range, you do need to have your data in order. Your smallest data item is 27, your largest data item is 99. So in this case, it's 99 minus 27, which I believe is 72. So that's the range of your data. So the range of ages of the people in this room spread over 72 years. That sort of makes sense, doesn't it? The other measure of spread that you might be asked to find is something called the interquartile range. The interquartile range. And this is your upper quartile minus your lower quartile. Now, whereas your range looks at all of your data and takes the biggest and takes away the smallest, with the interquartile range, what you're looking at is your data in quarters. Okay, now we already know that the median is the halfway point in our data. So the first quartile, which means the first quarter of your data, will be halfway through the first half of the data. So we've got 7 data items here, 1, 2, 3, 4, 5, 6, 7. So the middle one of those is going to be your fourth. And this is your lower quartile. And can you see that it is halfway through the first half of the data? Now, the same rule applies as we would have done for median. If we'd had that falling halfway between two values, we would take the halfway point between the two values, but here it doesn't, yeah, because we've got an odd number. So we've got 3 on that side, 3 on that side. You completely miss out this one in the middle here. You just ignore that one, yeah. This is the first half of your data. That's the halfway point. Same on this second half of your data. To get to your upper quartile, I'm going to go to the fourth data item out of this half of the data, and that's there. 3 data items below it, 3 data items above it. That one there is my upper quartile. So your interquartile range is your upper quartile minus your lower quartile. So in our case on this question, it's 64 minus 27, which I think is 37. So that isn't looking at the extremes of your data. It's just looking at that middle section of your data and seeing how spread out that is. And there's a spread of 37 years over the middle section of your data. Okay, it's ignoring anything at either end, and that's sometimes considered to be useful because you might have some real outliers, some real extremes in your data. So like having a 99-year-old person in the room, that's quite extreme. Most of the people in the room are nothing like as old as that, and therefore if we look at the interquartile range, that gives a bit of a better idea of the spread of the ages in the room. Now, the nice thing about all of these measures, is that you can calculate them for more than one set of data. So these are the ages of the people in a lecture somewhere. If you had another lecture going on in another room, you could look at the mean, mode, median, range and interquartile range of the data for the ages of the people in the other room. And you could work out whether on average the people in the other room are older or younger, whether the ages are more spread out or not. And that's the kind of thing they ask you in questions. Sometimes they ask you to compare one set of data with another set of data. So what you can do is calculate these sorts of things, especially the mean and the median, to give an idea of the middle value of your data. And then the range and the interquartile range to give an idea of how spread out your data is. And those two sorts of measures, a measure of your averageness and the measure of your spread are both really useful for comparing sets of data. Okay, there's just one more thing in this chapter that I want to have a look at, but make sure that you've got a note of all of these, so you could just pause for a moment if you need to. Okay. Last thing that I want us to have a look at in this chapter, we're going to go back to this idea of continuous data. And with the continuous data, hang on, I've just moved my board around a bit, I'll just make sure it's still on the screen. Yeah, with the idea of continuous data, we're going to have a look at a specific way of presenting continuous data. As I said, you don't do bar charts in quite the same way with continuous data. What you do is you present your data in a histogram. So we're going to look at a histogram. I'm going to write histograms here and just have a look at how we present data in one, how you can go from some data about some continuous data and how we can move from that to presenting it in a histogram. So a histogram is a bit like a bar chart. It looks like a bar chart, but it's actually presented in quite a different way. Now I'm actually doing an example from the book here because it's always good to do something that's a table in a book. So I'm on page 79 of the book, and I'm looking at question 5. I'm just using the data from that. So this table that I'm about to draw out has got lengths of cars in a car park, okay? So lengths are going to be L's, and the lengths of cars are in meters. I'll put that in meters, L for length. And these ones are between 3.4 and 3.8, and then 3.8 and 4.2. And between 4.2 and 4.4, and between 4.4 and 4.6, and finally between 4.6 and 5, so the longest car in this car park is 5 meters. So what somebody has done is they've gone and measured the cars in this car park, and we'll just have a look at how many they found in each category. So 20, 30, 18, 20 and 10. Now let's just make sure we understand what this means. So this means that they found 20 cars that were, look at the inequality sign, bigger than 3.4 meters and up to and including 3.8 meters. Soon as it goes beyond 3.8 meters, so 3.81 or even 3.801, we move into the next category or class. We call these classes, yeah? These are all different classes. And the inequality signs here, the strictly greater than, less than or equal to signs, tell you what happens with these numbers on the end. The 4.2, if you've got a car that's 4.2 meters, because the inequality sign is a less than or equal to, a 4.2 meter car will be in that category. A 4.21 car would be in that category, yeah, or class. Okay, now what we want to do is we want to plot the these lengths of cars against their frequencies. Now the problem is that these cars here come in different widths, class widths. This class width, so I'm going to write class width here, class width. This class width is 0.4 of a metre. This class width here, 3.8 up to 4.2 is also 0.4 of a metre. But this class width here is only 0.2 of a metre. And this one here is only 0.2 of a metre. And then we're back up to 0.4 of a metre here. Now, don't copy this down, gents. But if I was to just plot my frequency against my class, against my size here. So if I start at 3.4 and go to 3.8, 4.2, 4.6 and 5. What I would end up with, do not copy this down, gents. So it goes up, we go up to 30. So we go 20 and 10. If I was to plot my bars in here, so I would have, I've got 20 frequency from my 3.4 to 3.8. My bars will touch each other because they are, because this is continuous data. So we go straight from one category to the next, from one class to the next. 3.8 to 4.2, I've got 30 in there. My 4.2 to 4.4, I've got 18, so that goes sort of just halfway across there, 18, a bit lower. 4.4 to 4.6 goes up to 20. And my last category, 4.6 to 5, goes across, that's at 10. Now, I haven't done the world's most accurate diagram here, but if I was to just take a glance at this, I would say that this bar here looks bigger than this bar here, or at least the same size, yeah? And actually, that's the problem with plotting it like this. This bar here actually only represents 10, this one represents 20, and this one represents 18. Relative to each other, they look okay, but that one and that one don't look okay relative to each other. It's misleading. It makes it look as though there were lots of cars in the 4.6 to 5 category. And that's because the areas of these bars aren't representational of the frequencies. So what we're going to do is we're going to correct that, yeah? We are going to draw a histogram where the areas of the bars, a histogram has bars whose areas are actually proportional to the frequency. In order to do that, we've got to make the areas of the bars the frequency rather than making the height of the bar the frequency. So we are not going to have frequency on our y-axis. We are going to have something called frequency density on our y-axis, which you may remember. Now, frequency density is equal to, and you do need to remember this, it's equal to frequency divided by class width. Okay, so that's what frequency density is, and you do need that definition. It would be nice if you didn't write it on your y-axis, but I had to because I'm a bit out of space. Okay, so frequency density is frequency over class width. I'm going to actually put a column in for that on my table. So frequency density, and I'll put the formula up there as well, equals frequency over class width. I'll call that F for frequency and that's CW for class width. Okay, so frequency density for my first class is going to be 20 divided by 0.4. 20 divided by 0.4 I think is 50, yeah. So I've got 50 there. 30 divided by 0.4 for my 3.8 to 4.2 is going to give me 75. 18 divided by 0.2 can give me 90. 20 divided by 0.2 I think is going to give me 100. I think I can do that in my head. And 10 divided by 0.4 I think is 25. So what I'm going to plot on my histogram, frequency densities are going to go up the y-axis, and they're going to go between, I'm just going to move this whole axis along a bit actually, make it here so you can see it a bit more clearly. So that's going to go, I've got 100 there, I'll put 50 halfway, and I'll go for a 25 in around there and a 75 in around there. So this is my frequency density, and these are my widths of cards. No, it's lengths of cards, isn't it? Let's not do that. Lengths of cards. Okay, now my lengths of cards start at 3.4 and finish at 5. So 3.4, I'm going to go 3.8, 4.2, 4.6 and 5, and they're measured in meters. Okay, so my frequency density for the 3.4 to the 3.8 class is 50. So I'm going to draw it up to there. My frequency density for my 3.8 to 4.2 class is 75. 3.8 to 4.2. There we go at 75. Obviously yours will be a lot more accurate than mine. From 4.2 to 4.4, I'm all the way up at 90. So I'm just going to go halfway along there to make my 4.4. I'm going to go along to 90, make it look like it's not 100, but there we go. And then for my 4.4 to 4.6, 4.4 to 4.6, I'll put 4.4 in there so you can see it, to 4.6 is 100. So that's there. And finally 4.6 to 5 is at 25. Now my graph actually looks a lot more proportional, yeah? This block here has got a height of 50 and a width of 0.4. 50 times 0.4 is 20. That is the frequency represented by the area of that bar. This bar here has got a height of 75 and a width of 0.4. 75 times 0.4 is 30. And that does look, okay, not a great diagram, but that does look proportionally bigger than the 20 that's here. The 4.2 to 4.4, that's got a width of 0.2 and a height of 90. That's got an area of 18. This one has got a width of 0.2 and a height of 100, so 20 is the area there. And for this one here, width of 0.4, height of 25, it's got an area of 10. So my histogram of car lengths, histogram for car lengths, has areas of the bars that are proportional to their frequency. Yeah? And that's what histograms are all about. Now, sometimes in these questions, you're given the histogram and you're asked from your histogram to fill in a frequency table. So in this one, you'd have to say, well, I've got a class width of 0.4, height of 50, 0.4 times 50 gives me the area of that rectangle. My frequency is 20. Yeah? Over here, class width of 0.2, height of 90, 0.2 times 90 is 18. Fill in the gap on the table. And sometimes you get a half-finished histogram and a half-finished table, and you have to fill them in. But that's what you're basically doing with a histogram. Hopefully that's nice and clear. That's chapter 4 revised. We'll be doing some questions on this in our Teams lessons on Thursday.